Hello, and welcome to this NPTEL course on structural reliability, design, assessment, and safety targets. I am Boidurjo Bhattacharya, Professor of Civil Engineering at IIT Kharagpur. Let's start with why you should consider this course. The civil engineering community and structural engineers in particular, we have long recognized the role played by variability and incomplete information in our profession. These manifest themselves as random system properties, for example, random concrete strength or strength of steel, unpredictable loads, both due to natural hazards and caused by human activities like live loads, unpredictable deterioration of strength, for example, through corrosion loss and fatigue crack growth. Also, in certain cases, human errors at the design stage and the construction stage. And finally, in the mathematical models that we need to employ in order to analyze the structure, but the simplifications and idealizations that we put in those models. So together, they have a significant effect on the performance, the safety, the economy, and in certain cases, aesthetics of the structure. So ensuring adequate safety and functionality for all stakeholders in the presence of these uncertainties has long been a central objective of what we do, that is design and assessment of structural systems. And this course aims to give the students the ability to first model these uncertainties, estimate the risks of failure or non-compliance in general, making sure that these risks are contained within acceptable limits, and thereby ensuring safety, performance, and economy in structural engineering that best serves the interests of society. Now, who should attend this course? Students of mechanics-based engineering disciplines, civil, mechanical, aerospace, naval architecture, ocean engineering, mining engineering, and related disciplines. Our students of electronics, electrical materials engineering who are interested in structural performance, and they're in their third or fourth year undergraduate program, or students who are in their master's program, or doctoral students who are starting their research, as well as engineers and scientists in national labs and multinational companies with R&D facilities who are dealing with structural safety and performance issues. They should find this course useful. Because the principles apply equally well to terrestrial structures and structures that move, float, or fly, and equally well to large structures and tiny structures. Now, in terms of the prerequisites, the student should have completed at least their second year undergraduate curriculum in engineering with at least one course in engineering mechanics, and should have taken a course in basic probability and statistics, a course in linear algebra, and a course in basic calculus. Now, let's see if in one slide I could capture the essential features of what this course tries to do. So suppose I have a system which is a prismatic rod subjected to tension. It could be the cable in a suspension bridge, or it could be the tip of a nano indenter in an AFM. I know the purpose of this system. I know the environment it will be put in. I know its service life. I know how it behaves. What I want to do is to build or assess this system. So I know the properties. I know the input. I know what response I'm interested in, and there is an input-output model for the system which relates the input and the system properties with the response of interest. And I also have an idea about the system's capacity in terms of the maximum allowable response, which could either be an upper limit, one-sided, or it could be a range, which is two-sided. So that if the response exceeds this acceptable range, then I have failure. Now, because of the uncertainties that we talked about, this failure is an uncertain event, and there is a non-zero probability of failure. So if I know the randomness is involved, I would like to compute the probability of failure and then make sure that it is acceptably low. If not, then I must redesign the structure. And then obviously the question, which is common for all engineering activities, that is the solution economical? Now, I would also like to standardize the process if possible. Instead of doing this repeatedly every time, going through all the steps, can I codify, can I create a design code that would work in most of the cases for similar systems? Now things become more interesting and challenging if the load or the system properties, they are time variant. The loads could be dynamic, the system properties could be subject to degradation processes. Instead of just one failure mode, I could be interested in more than one. This particular system could be subjected to torsion, or if the load is not tensile, if it's compressive, I would be worried about buckling. Quite interestingly, if the models that I've employed, if they're uncertain, so I might have put too many idealizations that makes them inaccurate and random. So I would need to consider the randomness in the models as well. What if I have missed some failure mode or I don't know about? That would be another challenge. And I already said that, is the probability of failure acceptably low? But what is acceptable? How do I know what is? And so these questions we would like to ask and answer. And now think that, this is not a simple prismatic bar in tension, but something more complicated, like a gas turbine blade or an aircraft landing gear, or a tall building with thousands of degrees of freedom, which is subjected to seismic loads. So during this course, I hope to address these issues, and I hope you will enjoy it. Thank you.